Okay, and the other thing is yesterday I announced the final project. Okay, so that is the team-based project, but you have to submit the final report individually. Okay, so and also we have two presentation, first round and second round. And first round you have to present the paper content, okay, their core method and what those papers are tackling, and also their experimental result you have to summarize and present in the first round presentation. And actually, you have to submit the videos, recorded videos for that presentation, and we will watch that together in this lecture. And also, we will proceed up to 5-minute Q&A for each team. Okay, and the order of the presentation will be randomly decided. Okay, and also, in the second round, you have to analyze some of the weaknesses and strengths of those papers for tackling those tasks, and also summarize those things in the presentation. And also, you have to also do some few more evaluation studies. You have to plan what evaluation studies you will conduct and share the result to us. Okay, that's the second round. And also for the final report, you have to summarize all of the things, okay, in using your own word, not teammates' words. You have to write those results and analysis, the summarization for the papers by using your own word, okay, and submit it to the Blackboard. That's the final term project. Okay. And also, by this Friday, you have to submit which paper you will present. Okay. Uh, we are actually requesting you 3 candidate paper. Okay. Because we are wanting to prevent the same. There are 11 teams, but we are preventing those 11 teams present the same paper. Okay, we are encouraging all of the teams present different papers. So please submit the candidate papers, then we will adjust. Okay. Okay, that's it. And so for today, we will finish this. Any questions? Okay. The paper selection, they say by 17th of May. 17, sorry about that. April, 17th of April. Sorry. Yeah. I will re-announce that. Sorry about that. So by this Friday, my original intention was submitting those 3 candidate papers by this Friday. Okay, sorry about that. So last time we learned about this clip. Okay. So basically, this clip is aligning the image feature with the text feature. Okay, there are text encoder and image encoder, and the objective of this clip is to train this text encoder and image encoder. So some students asked me after the class whether there are training and testing phase, and this is the training phase, and the right is the testing phase. Okay. So here in the left section, we will train the text encoder and image encoder. And in the right section, using the the trained text encoder and image encoder, we will do inference. Okay. And as I mentioned previously, the previous CNN training, we have to estimate some probability, fixed dimensional probability vector as the output. So somehow we cannot easily manipulate the number of output classes. Okay. So we had to do image classification for a fixed number of classes that we designed during the training. But here, when using the clip, because the image encoder, their features are aligned with the text encoder's feature. And also in the inference step, we can input, we can easily extend the, I mean, the text text queries easily we can add here, okay? And extract some text features from the trained text encoder. And then by extracting some image features using the image encoder, and by comparing them, we can find the, I mean, the text descriptions for the images easily, okay? And that's how we can do the zero-shot image classification, zero-shot inference, okay? So when using this clip, we can easily extend our encoder towards the zero-shot classification task. And this is again showing the training pace of this clip. Okay, so actually we are we are how to say, increasing the scales of these diagonal entries, which is the measuring the similarity between the correct pair of text and images, and all the remaining things are measuring similarity to for the, I mean, how to say, the text and image pairs, which is not correctly paired. Okay, so somehow we have to suppress the values here and only increase the values for the diagonal entries. Okay, this could be easily implementable by enforcing the cross entropy laws for this direction first, okay, and then apply the cross entropy laws for this direction, okay. So actually, uh, this type of loss functions can be trivially implementable by applying the cross entropy laws twice for different axes. So for the low uh, direction, we can apply the cross entropy, and then column-wise, we will apply the cross entropy laws to enforce these diagonal values while suppressing the other entries. So this is the pseudocode for the training this clip. So this IFTF is the features extracted for image and text, and then we have to apply some normalization. And this is making them as the apply. This is for applying some softmax, applying some similarity between the pairs. And then here we are applying the cross entropy laws for different axes, and then average them in two directions. And we can easily implement the clip. Okay. And clip was trained using many image text pairs, which is obtained from the internet. Okay, so 400 million image text pairs. Okay, and there are two variants for the image encoder. So actually, resonant-based image encoder and also VIT, Vision Transformer-based image encoder they are having. And for the text encoder, they are only having the transformer-based text encoder. So Clip, they are providing some pre-trained image encoder and text encoder by using the loss functions that I explained in previous pages. And also, this is showing the power of the clip. So here, y-axis, they are showing the, I will explain this part first. This is the ImageNet score, which means training the overall network for the ImageNet data set and test on the ImageNet testing data. Okay, then this is the accuracy classification. This is showing the transferred accuracy, how to say, for the clip architecture. Okay, so I mean, each point here is denoting that, for example, this is the denoting the efficient network using efficient network architecture. If they could obtain better accuracy for in-domain testing data, when they are trained with ImageNet dataset and tested on the ImageNet testing data, their accuracies are like this, 85% using the same architecture. But if they are tested on different image classification dataset, their accuracy is becoming less. Okay, so originally they are for the in-domain testing data, their accuracy is around 85%. But if they are transferred to the slightly different data sets, their accuracy is becoming less. Okay. However, I mean, the CLIP method, this is CLIP VIT and CLIP ResNet, they are almost same for the in-domain testing data and also the out-of-domain data set. Okay, so even though they are transferred to the different data sets, their network's accuracy is almost same. That's the merit of CLIP, which is the text-aligned network. And this is showing the accuracy to the speed. Okay, so the CLIP is also fast. Okay, and this is showing also the generalization ability of the CLIP. So for some of the data sets, uh, I mean, this is zero shot CLIP means using the CLIP. So I already said that CLIP is trained with 400 million image and text pairs, and they are applied to some of the benchmark, image classification benchmark in the zero shot manner. Okay, if they are not seeing these individual data sets, their testing tests, and also the training sets they never seen before, but even though in that zero shot setting, uh, I mean, you can see for some of the data set, the CLIP is surpassing the state-of-the-art performance based on the ResNet 50 architecture. So these figures are showing that the Jerusha CLIP is surpassing the ResNet 50-based state-of-the-art models in these benchmarks. Okay, for some of the data sets, of course, because the CLIP is not seeing any data in those databases, I mean, somehow it is, of course, I mean, because it is not seeing the samples of those data sets, uh, maybe how to say it is natural, somehow natural, uh, that natural to say that the CLIP is not working better than those models, the ResNet 50 models, which has been trained using those data sets. This is somehow natural result because the CLIP is never seen this domain, this benchmarks data set before. Somehow it is, how to say, uh, not very bad for CLIP to be less than these in-domain trained models, their performance. But even in this situation, CLIP is sometimes better than some state-of-the-art algorithms, state-of-the-art models that is trained on dedicated benchmarks. Okay. And also, this is showing some other result showing the generalization ability of the CLIP. So this is the number of training examples for the CLIP per class. Okay, so this is the zero shot setting, and this is the one shot setting. Anyways, this is the few shot setting. Okay, even in that case, the CLIP that performs better than other alternatives. Okay, so this is showing that by aligning the deep learning models with the text signals, we can empower their generalization ability. And also, this is showing another merit of this CLIP architecture. Um, For example, this is the ImageNet data set having the real samples for the banana. Okay, but this is the ImageNet data set, but cartoonize their image samples. Okay, on purpose we can cartoonize some of the samples. And also even we can make this sketch version of the ImageNet dataset. And if we apply the ImageNet pre-trained ResNet architecture, and if we train this ResNet 101 architecture using the ImageNet dataset as the training samples, and then train on the ImageNet test dataset, which has the same characteristic, same attribute to the training benchmark, then their performance is like 76%. Okay, but if we apply those pre-trained ResNet to slightly different testing data, then their accuracy is becoming less. Okay, because the ImageNet, the ResNet 101 architecture is trained on these real images. Okay, so this model is not well generalized to cartoon images or the sketch images. Somehow this is natural thing. Okay, so their performance is becoming less. But zero shot clip, their performance is retained. Okay, even though their property, the image property is slightly changed, even they are becoming, the accuracy is becoming better, okay, and not losing much accuracy, okay. So that is the clip. So by aligning the vision models with the text, we can increase their generalization power, okay. And this is some weakness of the clip, okay. So zero shot performance, it can perform the zero shot classification, but sometimes it is below the state-of-the-art architectures. That is the weakness. And it is poor on some out of data, distribution data, on some of the benchmark, and also weak on some abstract tasks. Okay, that is some weaknesses remained in the clip. And adversarial attacks, it is weak, and social biases, because it is trained with internet scale data sets. If the benchmark itself is having some bias, then the clip is also having some bias. Okay, that's the weakness of the clip. And another important weaknesses is clip is can be applied to image classification only. Okay, so there has been some attempt that extend this clip towards the object detection task. Okay, so previous clip is not working well for the sum of the bounding boxes generated from the whole image. Okay, so this paper vision clip is extending the clip towards the object detection task. Okay. So this is some method for that. So this is original pre-training steps for the clip. Okay, but there are another steps required for extending the clip towards the object detection, which is the region text pre-training. Okay, there are one text encoder. This is the language L. This L box is denoting the text encoder, and this is the original clip's visual encoder, image encoder. And we in this paper they are proposing one another visual encoder, which describes the regions. Okay, rather than the whole image, they are describing the regions. Okay, so language and visual encoder of the clip, they are aligning the whole image with the text descriptions. That's the original way of pre-training the clip. But here, what they do is they are describing the regions. Okay, and also they are extracting some regions instead of the whole image, and then the new region-wise vision encoder. Okay, that's the uh, I mean, how to say, the way of extending the clip towards the region. Okay, and by doing this, they can apply the clip to the object detection task. Okay, okay. So now they are describing the small, which is full desk clip. Okay, that's also doing the similar thing. They are I mean, extracting some region-wise regions and then apply this same, how to say, the contrastive learning, okay, to train those vision and text encoders. Okay, I will pass this. And the other, I mean, important pipeline is the grounding Dino. And Dino, we will learn about that later lectures. But Dino is the extension of the DETR. Okay, so I already told you that DETR is the transformer-based object detection, but in their object queries, there are some weaknesses. Okay, so object queries of DETR is not having any meaning. Okay, semantic meaning, there has been no semantic meaning in object queries. So that's one important weaknesses of DTR, and that makes the DTR training hard to converge. Okay, so there has been some schemes to add some semantic meaning to, especially the spatial meaning to object queries of the DTR, and also other techniques, other skills are added to the original DTR, and eventually the that becomes the Dino algorithm. Actually, there's another Dino algorithm, but this is object detector. Dino, the other Dino in vision domain is the feature extractor, but this is the DTR, updated version of the DTR. Actually, CVPR 2024, maybe, yeah. And grounding Dino, that is combining this state-of-the-art transformer-based the object detector, whose name is Dino, with the text signals. That is called as the grounding Dino. And actually, it's published in some of the CVPR, maybe CVPR 25, it is published, accepted in that conference. And when this, I mean, the is also aligning text signals to, I mean, the vision models, okay? And by doing that, we can have some new benefits. For example, previously, what we have done is the closed set object detection, which means because we train the object detector with fixed, how to say, the predefined categories, okay? So the detector is working for these predefined categories, okay? So we can only estimate the person classes and bench classes which were pre-trained, predefined in the benchmark. Okay. For example, we are using Microsoft Coco dataset having like 20 classes to train our object detection algorithm, and then apply this model to the new image to classify those, to, how to say, detect some object, predefined class object, okay? That's the closed set object detection, but we can do this type of open set object detection by aligning text signals to the vision models, okay? For example, now we can uh, detect new classes which were not originally contained in the training data. Okay, so for example, the year of the lion was not defined in previous benchmark, but because we now align the text signals to the vision models, we can do this type of things. And World Cup is also something which is not defined in the previous benchmark, but now we can detect this type of World Cup. Okay, and also among the lions, we can detect, we can further detect some descriptional classes. For example, among lions, we want to detect the leftmost lion. Okay, so now we can detect this lion, which is located in the leftmost position. The left lion we can detect. Okay, and also among these persons, we can detect the bottom man with his head up. Okay, so now the, how to say, the classes that we want to detect becomes more descriptive. Okay, So that's another merit of aligning the text signals to the vision models. Okay. So this is the architecture of the grounding Dino. Okay. So this is the overall model pipeline. Okay. So this is basically similar to the DETR architecture that we have learned. Okay, so there is some CNN architecture. So from the input image, we extract using the CNN feature extractor, we extract some initial feature and then fed this to the transformer encoder. So this is the transformer encoder. And that roles as enhancing the feature, okay, this is the initial feature, and by applying self-attention mechanism in the encoder, we are enhancing those feature, and this is the enhanced feature, okay. And then using the decoder, we originally mapped those feature to the bounding box information and also the class information. That was the original DTR, okay? But here we are having another text stream, okay? This is the text stream, okay? This is the image stream, and this is the text stream, okay? So here, what they input is some text signals. So here we are having some text signals, okay? And then in the feature enhancer, this is the magnified version of feature enhancer, okay? So now we are somehow mixing the image feature and also the text feature. This is the text feature extracted from the text encoder, and this is the image feature extracted from the ResNet, maybe. And in the encoder, we are somehow mixing those text and vision, the image features, okay? That's happening in the encoder side, okay? And then and also here, the cross-modality detector, we are mapping somehow here again, we are mixing those text signals and the image signals and map it to some, the feature. We are not directly mapping this to the class information and also the bounding box information. Instead of doing that, we are still mapping them into the some of the form of the features. And then here we are getting the text feature, and this is the somehow text combined vision feature, okay? And then here, what they do is they are doing the similar things as the clip, okay? They are training this part by aligning only the diagonal they are increasing the value of the diagonals because that's the correct pairs, image and vision pairs, and suppressing all other entries. They are applying those type of contrastive loss here, okay? And somehow they are aligning text and vision at the end of the DTR, okay? And by doing this, they are extracting some vision feature which is aligned to the text feature, and they can align each region information to this type of text signals at the end of the DTR. Okay, so this how extend the DINO architecture, which is the transformer-based object detector with the text signals. And this is another schemes, but I think this is minor. The important ideas are contained here. Okay, so I will skip this part. Okay. And also nowadays, so far here we are doing some text-aligned object detection I introduced, okay? And also we can do some of the text-aligned segmentation tasks, okay, using the same architecture, okay? And this is actually another foundation models. A foundation model means the big, huge architecture which can be generalizable. And this same actually segment anything model, and we are calling that as the SAM architecture. So this is also this is segmentation anything model, which is called as SAM, proposed by Meta, and they are collecting lots of segmentation data sets, almost over 1 billion masks, and train this architecture. Okay, and also this is based on the transformer-based architecture, but basically their architecture looks like this. So we can input some of the prompt, okay, and that prompt could be some initial point or some bounding boxes, or some rough segmentation masks. Okay, any of these rough prompt can be here, and also we can input some of the text prompt. So here, this is example of the prompt, and also the model is also inputting some input images. Okay, and the model now map it into the valid mask. Okay, that's the same algorithm. They are building this type of defining this type of model architecture and using over 1 billion masks and using many GPUs. They train this model, and that's called as the foundation model for the segmentation application nowadays. Okay, so this is more detailed architecture for the same architecture. This prompt, one either of these point, bounding box, segmentation, initial segmentation, or text, they are also via encoder, they are mapped to the feature, and images are also mapped to the image encoder. And this decoder is outputting some masks. Okay. Okay, this is the image encoder. Again, the same figure. So from the input image, we are applying image encoder, and those prompt can be mapped to the feature. Okay, point, box, text, they are mapped to the feature using separate encoders to the masks. Okay, and masks that's similar to the 2D, that's in the form of 2D signal. So they are converted to the feature via the convolutional layer, okay, and mapped to via decoder. They are actually estimate 3 candidate segmentation masks. So why 3 is experimentally they are validating that the 3 is better than in performance. That's better than 1 candidate segmentation mask. So they are estimating the 3 candidate masks. Okay, and also their architectures are mostly using the transformer. Okay, and some of text signals they are using text encoder, clips text encoder, and masks they are applied with convolutional layers and so on. Okay, and this is a segmentation result. Okay, so any images following this prompt, they are providing some candidate segmentation masks. So here, that explains why they use 3 candidate. Why they are not here maybe. This is not okay. Sorry. So this is showing how many point. I mean, I mentioned that previously. I mentioned that we can give some initial point as the prompt. So given some images, if there are human here, then if users uh, po give some point here, and then just using this point as the prompt, the SAM can detect the segmentation mask, fine segmentation masks for this person. Okay, so that's why we are giving this type of prompt. I mean, rather than giving this fine segmentation masks, giving these 3 point locations are easy for humans. Okay, so we are wanting this fine segmentation mask, but gathering this fine segmentation mask is difficult for humans. So we are giving only rough 3 point to the model, and the model can, detect the fine segmentation mask. Okay, and depending on the number of point, their segmentation mask quality is becoming better. Okay, this type of, and also how they define those point. Okay, so uh, center point is how to say the default thing, but using some different method, the automatic method, they can also giving some point signals. Okay. Okay. Anyways, here also they are showing that compared to the dedicated segmentation models, okay, especially this rhythm was the state-of-the-art segmentation algorithm, which is not aligned with the text signals. Okay, and a lot of benchmark rhythm, get better performance than SAM. But even though SAM was not pre-trained on dedicated data sets, they are getting better performance than this dedicated algorithm. Okay, so that's showing also the power of the SAM. Okay, okay, so that's another foundation models that we call as SAM, and this method can also be further aligned with the text. Okay, so even though the original SAM can provide some text encoder, okay, but their how to say power of aligning with text was somehow weak. Okay, even though they can, of course, uh, I mean, input the text prompt as input, but they are not uh, that's not main feature of this SAM. So they can also input some other types of prompt, and the SAM is not uh, how to say focused on this text alignment. But if you use this language SAM, LangSAM, we call this as the LangSAM. Uh, then SAM can also work better for some new unseen classes. Okay, so that's LangSAM is the combination of SAM with the grounding Dino algorithm. So grounding Dino, we already seen that it can detect some new classes which is unseen during the training. So grounding Dino can detect some object in the image which is unseen. For example, the World Cup or the left lions can be detected using grounding Dino, and they are having, how to say, this type of bounding box information, and then we can further apply the SAM after this grounding Dino's output. Then we can detect any person or any other object uh, which can have more descriptive, uh, captions. Okay, so from the image, using the grounding Dino, we can detect some descriptive object first, and using this bounding box as the prompt, we can finally generate their segmentation masks via SAM. Okay, that's the lang SAM. Okay, and also SAM originally proposed in the year of 2023, but now SAM is having version 3. Okay, so their performance is getting gradually better. Okay, so their performance is now very good. Okay, that's the some algorithms that is aligned with text signals. Okay, so now computer vision domains, their algorithms are getting can perform some open set object detection, segmentation, and image classification by aligning them with the text signals. Okay, and another important direction for these visual language models are generating images from the text. Okay, so that they are called as T2I models by abbreviating this text to image generation task. Okay, so this is the some new tasks defined in computer vision domain. So given text signals, they can generate images which well aligned with the input text. That's the text to image generation task. And actually, this DALI is another famous application uh, published by the OpenAI. Okay, but nowadays, this feature is it's not well known for uh, AI domain because I mean this feature is merged to some VLMs. Okay, so now we don't have this separate image tech T2I modules. Okay, but they are merged to VLMs. So now ChatGPT is also generating images given text. But previously, this DALI was also the separate algorithms. Okay, this is the independent T2I generator. So given this type of text, they can generate some images that best describe this text. Okay, that's the T2I tasks. And this is another. So this is the text input. Okay, and this is the DALI, their result. Okay, previously the GAN algorithm that we have seen was the state-of-the-art algorithm for this type of T2I generation, but their quality was actually bad. Okay, they are not actually describing giraffe correctly, but this DALI is describing that well. Okay, so the version DALI is having version 1 to version 3. Okay, and version 1, they are using the transformer as the autoencoder. So that's actually similar to the architecture, encoder-decoder architecture that we have seen before. Okay, but previous encoder-decoder architecture that's composed of the CNN, the convolutional operation, but now the difference is this DALI is having those VAE structure using the transformer as the basic block. They train this VAE on image data only because VAE, their encoder and decoder, and the same image, if the image is fed to the encoder, they are mapped to the feature here, and the features are mapped to the image again, and they apply supervision, the original image as the supervision to the output of this VAE, which means using only image data, this encoder-decoder architecture, which is the VAE, are trained to generate images, their original image again. Okay, so this VAE can be trainable using only the image data. And then what they did next is in the first step, they are training this VAE architecture composed of encoder-decoder using only image signal to generate themselves the input images again. And they align text feature in the middle of this feature. Okay. Then there becomes new paths appeared. So from the text, they can now, using only decoder, can generate images. Okay, that's how this DALI make the architecture works for the T2I generation tasks. Okay, so they are first uh, using many image only data, train this encoder-decoder architecture, and then align this middle feature to the text features, and then apply those architecture for the T2I generation tasks. Okay, that's the DALI architecture. The main thing why DALI works better than previous GAN method is they are using many data sets and also using the transformer-based architecture. Okay, that's the difference. And they are producing better accuracy. And but DALI version 2, what the main feature is, they are using diffusion algorithms. Okay, so previously we used GAN algorithm, but nowadays every generative AI is using the concept of diffusion. So DALI version 2, the OpenAI is starting to using the concept of diffusion, and that's why they could have better performance from the DALI version 2. And I want to give you a very brief concept for the diffusion model. Actually, to properly understand this diffusion model, you have to take maybe few more lectures, okay? But you may have to take DGM, Deep Generative Model classes in AI graduate school. But I want to deliver very brief, explanation for this diffusion model, okay? So this VAE is composed of the encoder and decoder architecture, as I mentioned previously. So the input of this encoder-decoder architecture is the image, and their output is also the image. And decoder that's composed of if their main operation is the CNN, then we can upsample it via the transposed convolution operation. Okay, that's the VAE. Okay. But the diffusion, that's similar, very similar, having the very similar concept to the VAE. Okay, that's in the sense that it is generating some feature, okay, first, and then they are making the original images after that. Okay, in that concept is very similar to the VAE. But what they did for their detailed process is becoming slightly different. Okay, what they do is they are applying some noise to this part. Okay, so from the X0, which is the original image, they are add some noise. Okay, they slightly give some Gaussian noise. Okay, and then Z becomes the complete noise. Okay, so normally we do this process by 1,000 steps. Okay, we gradually add the noise. Okay, and then make it into the complete noise. There's no how to say network involved here. Okay, VAE, we are using encoder to make this X, to map this image X to the feature latent space G. We are explicitly applying the encoder architecture. But here in diffusion, we are just adding some random Gaussian noise, and we are not using any networks here. But the network is used for inverse step. So here we are calling them as the forward step, and here we call that as the inversion step. Okay. What they do is we are denoising the images. Okay, here, and from X2 to X1, we are applying some network, some inversion network we are using, and those networks are actually trained. Okay, so here in the inversion step, we are using some network, and those networks are trained to denoise the noised features to unnoised feature. That's actually the diffusion model. And surprisingly, this diffusion model is working better than this VAE or the GAN models that we have learned. Okay, so mathematically, they are somehow proven why this diffusion is working. And even though their how to say the actual operation is seemingly weird, but they are working. Okay. But originally, the diffusion models are applying this noise to the input images and denoising the original images themselves. Okay, that's original diffusion works. But LDM, this means the latent diffusion models. Okay. And this is, maybe you have heard about the stable diffusion. Okay, that's also some, how to say, the famous diffusion-based T2I model, which is actually the state-of-the-art T2I model before the VLM. Okay, that's uh, somehow, I mean, famous before VLM. I mean, that is based on this LDM. Okay, and what they do is they are called as latent diffusion model in the sense that they are applying this diffusion process in the feature domain. So this is the original image encoder, image encoder, and they are first mapping those images into feature domain, and they are applying this diffusion process, which is the forward denoising process and denoising process using the UNet architecture. UNet becomes the denoiser here. They are applying this forward step and denoising step, the inversion steps, in the latent space, which means the feature space. Okay, so that's why they are called as the latent diffusion models. Okay, rather than applying noise and rather than denoising images themselves, they are doing that in the latent space. Okay, that's why they are calling them as the called as the LDM. Other than that, any other things are same. Okay, this is standard diffusion models, diffusion laws. Okay, they are. This is applied for denoising each step. This losses meaning their output becomes similar to the denoised. I mean the noise that was added to the forward step at each step. Okay. And after denoising the feature, they are applying decoder and reconstruct it to the original image space. Okay, that's the LDM, and this is better than original diffusion models in the efficiency. Okay, so applying noise and denoising the noise in the image space that takes a lot of resources. So by doing that, by performing that in the latent space, they can make them efficient and not losing much information. Okay, the latent space is easy to deal with. So LDM performs actually, in practically, LDM performs better than the original diffusion, and they can make the stable diffusion. Okay, but nowadays, this is also merged to the VLMs. Okay. Okay, so DALI version 2, that is actually similar to DALI version 1 in the sense that they are somehow using text encoder and image encoder. Somehow these architectures are similar to VAE, which is used for DALI version 1. But now they are applying clip objective instead of the VAE rules. Okay, and they can explicitly align the text encoder and image encoders. Okay, and then they are using two types of prior, and first is the diffusion, and the other is the autoregressive prior, which is the transformer prior. But in practice, in experiment, they are validating that the diffusion prior works better. So actually, DALI version 2, they are actually using clip loss and diffusion loss. Okay, that's why this DALI version 2 works better than DALI version 1. And also, of course, they are using many samples, but they train text and image encoder using clip objective and train decoder using the diffusion loss. Okay, that's the DALI version 2. So here they are using two types of prior, autoregressive and diffusion prior, but diffusion prior is producing better accuracy. Okay, So sometimes we call this as the on-clip, and because this DALL-E version 2 is doing the other directional things compared to the clip, but diffusion prior, that's performing better than autoregressive prior. So this DALL-E version 2 is exploiting two things, clip loss and diffusion prior, to be better than other T2I models. So this is on comparison to other things. This is the DALL-E version 2, DALL-E version 2 and other models. Okay, so given this text description, they can generate images, but DALL-E version 2 is producing better quality images. Okay, but still, DALL-E version 2 is having some problem, which is called as prompt following issue. Okay, so if the text is becoming long, and it is becoming complex, then sometimes this DALL-E version 2 is not following the prompt. Okay, so that's the problem. So there has been some attempt to improve this type of issue by using some LLM. So currently, by DALL-E version 2, we are sometimes depending on the clip encoder. But clip encoder, that's power is limited, but actually language models, they are providing better capability for understanding the languages, the text sentences itself. So there has been some new T2I model that embed these large language models as the text encoder rather than this clip encoder, which is called as ImageN, okay? And they are producing better performance for long sentences. And also there has been some new benchmark proposed, such as the draw bench, okay, having some long and some complex text description and rare word and some misspelled prompt, okay. There has been some benchmark for this type of things, okay. And then DALL-E version 3 was trained on this type of complex data set, and they can be can generate better images even for this type of complex text descriptions. Okay, so they improve the performance, okay, by involving some image captioners. They are involving some better text encoder and also trained on long sentences. So this DALL-E version 3 is having better capability for the T2I generation. Okay, so this is the end of lecture. So conclusion, how to say, in the former part, we have seen some new computer vision models that is aligned to the text signals. So they can be robust to the generalization. Okay, so they can be doing the vision tasks in the zero-shot manner. Okay, so task agnostic and few-shot performance they are providing. Okay? They can be obtained by aligning their vision models to the language signals. Okay, so and actually nowadays we are using VLM. Okay, we will also see this more in the later of this lecture. So so far we have learned clip text encoder based approaches, but later we will also see some of the VLM based ones. Okay, so now Vision Research doing some multimodal training is giving us very promising way to increase the performance and especially the generalization ability. Okay, that's the conclusion. Okay. So for today, we will finish here and see you this Wednesday. And actually, we have quiz one in this Wednesday. Okay, see you guys.